Hi. So this is a talk about distributed systems architecture. I usually start talks like this trying to justify why that's important. It turns out that these days it's not the hottest topic in the world, although I hear it's becoming more popular again. People are into machine learning. People are into building apps like social networks and games. I don't think I need to justify it to this crowd. I think you all know that no matter what you build, you need a distributed system to serve it. Right? You could build the best social network in the world, you could build the best game in the world. If the backend can't handle the load that your app is receiving, you're going to have problems. Right? And so I care a lot about this. A company like Bloomberg obviously cares a lot about this. And so I end up finding myself talking about it a lot. I also didn't appreciate it myself when I was a new graduate. I wanted to write code. I wanted to have a problem, I wanted to do it. I thought that the challenge was in being able to write the code in the first place. Right? That was the challenge. It turns out, eventually you discover you can write any code, and the question is about what code should you write. And if you guys play Dungeons & Dragons or you're into role-playing games, it's like the difference between intelligence and wisdom. And so nowadays, I like to think about what I'm going to write a lot before I write it. And that's why I'm coming here to talk about architecture. Why here, though? Right? Why did I pick an SRE conference out of all the conferences to go to and talk about this? Well, I actually like that this is the theme of the conference. And I want to give you my take on how SRE fits into organizations. I don't think it's a unique take, but I have a slightly subtle way to point out, I think, what the real differentiation is. And so let's do that. So we all have product managers, right? I was a feature developer for years. We all have feature developers at our companies. I think what mistake we make is that we just call them the engineers. We're not engineers. We're SREs. Wrong. All right, I'll tell you why that's wrong later, but I call them feature developers. And so product managers apply feature and time pressure to the feature developers, and then they produce features and hopefully not tech debt. But as we all know, that just is an unavoidable thing. And then we come along, the SREs, and we implement SLIs and SLOs, and we get some feedback loop going, and we try to improve performance and reliability while hopefully reducing tech debt. Although I know that a lot of people in our role don't have the ability to necessarily write code all the time, so that can be challenging. But I actually disagree with this alignment. I think that all developers should use SLIs and SLOs and get involved in this cycle, right? I don't know why that's an SRE-only tool. I think the SRE book was helpful in proposing new tools. I think it failed in defining that only SREs do it, is my personal opinion. So what is the difference then? The difference is that we are decoupled from feature and time pressure. Now, we might have our own features and time pressures originated from ourselves, but it's not coming from product. And so to me, and at Bloomberg largely, this is the situation we're in. The SREs are engineers just like the feature developers. But without that feature and time pressure, we have the luxury, I would say, to focus on the system for its own sake. Right? And I think that's something that feature developers, unfortunately, don't have the opportunity to do. I think the people in those roles are trying their best, and it's just tough to meet the needs of the product managers without creating tech debt sometimes. Okay, so I think this goes some way to establishing why I think that we should be talking about software architecture at an SRE conference. What I'm here to talk to you about specifically is how to build truly stateless systems. I'll explain why this is the behavior I picked later. But I believe statelessness is one of the most powerful behaviors a thing can have, right? A system, a component, anything. I want to define statelessness because I think there is some, I don't want to say lack of clarity, but there are different interpretations. For example, in REST, representational state transfer, statelessness is listed as a core tenet, but it's only discussed in terms of client state. 20 years ago when I started engineering professionally, Java was the big backend monster, right? It was the big gorilla in the room. And Java servers usually stored a session for a user on a specific host, which means if that host went down, you would lose all your data, potentially. And it meant that you really didn't have a farm of resources that you could use equally for any user. And so REST really changed that paradigm by saying that no, the client state should go on the client so that no matter what backend your client request hits, you can still service it. And that's fantastic, but I go further than that. I say that a stateless component is one that always returns the same output for a given input. It's effectively a calculator. And now a lot of people should be saying, well, Pete, that's ridiculous. Very few things are pure calculators. Yes, if I was literally doing A plus B equals C, this is easy. You can't do this with real systems. And I think you can. I think that there are patterns that you can apply to a lot of situations. I think software engineering, to some degree, represents mechanical engineering in the 1800s. Remember those pictures of the bicycles with a huge front wheel and a little back wheel? No one thinks that's a good idea anymore, but they tried it. And I feel like that's the state that we're in today with software engineering. A lot of companies don't necessarily have great designs, but it works because they were first, they got a market position, and they're like going through it. But I think that we're learning over time, and I hope, when I come here and talk to you guys and throughout my career, that we can kind of establish some patterns that really help build good distributed systems. Heck, we all know that software is terrible, right? Like every day I use my phone, I feel better about my professional work, right? So we have progress to make. I think containerized services is one of those things. I think it's a real winner. I'm not sure about Lambdas yet. Like maybe they're the next thing. I don't know. But containerized services is a real step forward, and virtual machines before it was a real step forward. So I think we're getting there. I want to talk about stateless systems, and specifically truly calculator-like stateless systems. Why is statelessness so important? Well, statelessness gives you two really important high-level behaviors: cacheability and testability. If something returns the same output every time, it's almost by definition cacheable. And if something gives you the same output every time, it's almost by definition testable. And those things give you performance, they give you scalability, they reduce cost, they let you iterate quickly, right? Testing is a pain. Nobody likes it. You always get that one guy who likes unit tests, but otherwise nobody likes this stuff. And it makes your system more reliable when it's easily testable, right? So I think we can all agree we want this behavior, and most people that I meet just often accept that they can't do it in as many contexts as they like, right? And so if I do anything here today, it's to encourage you to try and do it in contexts that you didn't previously think was possible. Okay, so the title is Caching Entire Systems Without Invalidation. It's not the best title for a talk on stateless software engineering, but a coworker of mine and I argued about this for literally weeks, and I'll show you why this is what we ended up with. Because you can break down this discussion about statelessness into two portions: how to cache without invalidation, and then how to cache entire systems, and they stack on each other. All right? And anybody who appreciates the challenges with invalidations probably came to this talk, and so I appreciate that. Okay, so the first section is caching without invalidation. This is a famous quote by Phil Carlton. There are two hard problems in computer science: cache invalidation and naming things. And I love this quote, because there's a lot of complicated stuff in computer science. He didn't pick any of those. He picked cache invalidation. And naming things is a joke, right? It's serious, but it is really a joke, right? Of all the topics in computer science, this guy picked cache invalidation. It's crazy, right? In fact, modern microprocessor design is largely driven by cache invalidation around the various caches in the processor and the RAM subsystem, right? It's a huge component of that. So I picked a tough topic. In order to discuss this, let's take a trivial example of a function. Now, I know this is a little bit too basic, but it's a good example because it has some state in it that in normal systems, we kind of just write off as being too difficult to make stateless, right? So this function takes a username or user ID, takes some indication of the user, and then calculates how many days old the person is. You could naively implement it like this. You have a client that calls the days old function, you put a cache in front of it, and then for the sake of conversation, let's figure out what state is inherent in this operation. In this operation, there are two important points of state. The user information, right? What the user's birthday is. So in that user database is my birthday and all of yours. I don't actually have your data, but if I did, it would be there. Today's date is also needed in this calculation. And I really wanted the first example to highlight today's date because we oftentimes kind of ignore time. And one of the verboten things in my group today that we often catch during code reviews is people calling time.time in Python or datetime.now. That's evil. You don't access time in your code, right? At least I don't think you do if you want to have a stateless system. So I think this is important. It's a very simple operation, but it really uses two very important pieces of state. So what happens if you build a system this way? Whenever today's date changes, that cache is no longer good. So how do you deal with that? You could set a time to live cache. I don't love time to live caching. I think it has its uses, but it's not as good as true immutability. So yeah, you could do that. You could actively clear it when midnight happens, which is kind of crummy. What happens when a user's birthday changes? The same thing happens. The cache is now stale, so you have to clear it. You end up with something like this, right? Where if the client calls the user update service to update the user database, you have to clear the cache. And you have either a date change cron job or you have some sort of time to live caching to clear the cache as well. This is complicated, right? In fact, this isn't a cache at all, in my opinion. This is a just-in-time database. Whenever someone is actively messing with the cache contents, I don't think it's a cache. I think it's a just-in-time database. And if we called it that, it would help in kind of understanding what we're doing. So can we make this simpler? I think we can. What we can do, oh, sorry, take a step back. I might have originated this quote. I don't think so. It's such a common statement that I think someone else has probably said it. But if no one has said it, I claim it. The only good cache invalidation strategy is no strategy. Cache invalidation is hard, so we're just not going to do it. Right? This is how you design stateless systems. You don't invalidate caches. So how can we restructure this problem to avoid having to do any cache invalidation? We can do this. We can separate the operation into two sections. So we maintain this days old that takes a username. And look, I'll be honest. That's a rational function signature, right? Like if someone proposed calculating how old someone is, that's what I would have picked. But underneath the covers, I have a version of the calculation that takes two discrete inputs that have no state attached to them. The actual day that the calculation starts and ends at. Right now, I think this is important because no one's going to do that naturally, right? You have to kind of be told that that's valuable. But what you do is you move the cache over there. So now what happens is, request comes into your stateful days old function. You pull the user's birthday from the database. You fetch today's date somehow, and then you pass those to the function, right? And now this function is perfectly cacheable. If I change my birthday over and over and over again, cache is still good. When the day rolls over, the cache is still good. Nobody needs to touch that cache ever. This might also, you might say, well, Pete, wonderful. You just made it so that the user database is uncached, and so you're going to have all this traffic to the user database. Yes. That's by design. Nobody wants a cached user database. If you ever used a product where you changed a setting and it didn't take effect immediately, you wouldn't like that product. This is a design feature of the system. User settings databases should not be cached. Now that said, I have cached a user database before, specifically when dealing with enterprise, like business level traffic, where I know that they're not touching user settings on a day-to-day basis. And even then, I set the TTL to 1 minute. We have a customer who makes like 1 million requests a second, right? And so that 1 minute cache is saving me 999,999 requests, even with such a short temporal cache. Okay, so this is simple, right? But how do we, let's talk about this a little more. What's really going on here is that we're factoring our application into two stages. A state gathering portion and what I call the immutable zone. You could call it the stateless area, right? But the idea is that you gather all the stuff that could cause an operation downstream to change its results, and you resolve that in the beginning, and then you pass them by value into the back end, right? And so this is the pattern. Just for like discussion's sake, I have here 3 different versions of that method that take different arguments. And I want you to see how interface design really matters. The cache characteristics of this operation have almost nothing to do with the operation itself and everything to do with the interface design of the operation. If you take the to and from date, you have a perfect cache lifetime of forever. There is no invalidation strategy ever needed. If you take the birthday, you're actually doing better because now you don't have the user database in play. But you still have some issue with like tomorrow, what happens at midnight. I don't really recommend this because there's time zones in the world, and like those are kind of wacky. So, and then you have the one that's the most obvious to me at least, which is the one that takes a username. And that one's really bad, right? It's the cache lifetime's only good until the birthday changes or midnight. And so you need to like actively invalidate it when the birthday changes or also invalidate it due to time. So if I hope there's any point that is obvious here, it's that interface design really, really matters. So just to iterate this point again one more time, I want to walk through what happens inside the cache in these various situations. So this is my cache, and you can see that we have the days old function with its parameters, and I reverse those dates so that they're in European format for those of you who are European, and it turns out there are a lot of Americans here, so someone is not going to be happy. But my birthday is September 6, 1982. Today is October 27th. I am 14,661 days old. What if that was a typo and I want to change my birthday to September 1st? We get a new entry in the cache, right? And that's like the brilliance of these kinds of interfaces, is that the cache now contains both entries, which means if I change my birthday back, it's still good. It means that if there's another user with the same birthday as me, it's still good. And this is an important detail because a lot of people I've heard criticisms before that these by value patterns don't work because you don't get a lot of cache commonality. But I think you do actually. There's not that many days of the year. And for most situations, it's like that. Same thing with like currencies, you know? If a user has to select a currency on your website, there's only like, really 6 or 7 that probably get used in your, especially now with the euro and now the pound. But so this is why this kind of cache behavior is good. The cache is resilient in the face of people changing their settings back and forth. By comparison, if we look at the username case, what happens if my birthday changes? Right? This value is not right anymore. The system will just use it naively, not knowing that it's wrong, right? So you have to actually erase it and put a new entry. And this is like really what's bad. For the sake of completeness, the TTL case has the behavior of the fully immutable situation where you have both entries side by side in the cache. So it's not terrible, but again, you have to expire it at midnight. How are you going to do that? So acceptable, but not great. So what have we learned so far? I think that true statelessness reduces complexity. Remember from the first diagram, we removed a lot of edges for clearing the cache when these results became invalid. Any cache invalidation is bad. Interface design drives caching characteristics. And this is, I think, a really important one that might not be as obvious as some of the others. Stateful interfaces can be converted into stateless ones internally, right? I think it's best if you expose stateless interfaces, especially if you have a small number of customers and they're also enterprises who can kind of understand why you're doing things that way. But if you can't, you can still expose simple interfaces that take things like usernames, and then in the very first layer of your system, resolve all that stuff into discrete values, and then have a stateless area behind it. And so, yeah, factor systems into stateful and stateless layers. Okay, so sounds simple for such an easy operation. How do we do this for like a whole system, right? The system's deep, it's wide, it's not trivial like what we just saw. How do we extend this further? Really what we just did is we learned how to control for two types of state: small databases and wall time. That's really what we just did, but we can apply similar patterns to other situations. Big databases are one that I think a lot of people are out there probably saying, like, great, Pete, what do you do with the 40 terabyte database? What do you do when software versions change? What do you do with external systems? So let's talk about those. I didn't mention this before, but one of the reasons that I think keeping small databases, specifically user settings databases, outside of the cached area is because small databases are somewhat easy to replicate globally, right? You have like an out there. If you have a lot of user traffic, you can distribute them. You can get a CDN to distribute that database. Yeah, it's a little wonky to deal with rights, but user settings don't really change all that often. So that's often an acceptable strategy, but that doesn't work for big databases. So for the purposes of discussing these more difficult concerns, let's imagine a situation like this. I think this is a pretty common diagram, right? You have some clients. Clients call application-specific services. So you have one client uses an API. Another client uses a web interface. Both of those use a shared business logic service. Good design, right? You want to share that stuff. Then you have a database access service in front of your database. Now, the database access service is not important at all for the purposes of this conversation. I just believe strongly that every system should front a database with a service to isolate its details, and so I refuse to make a diagram without it. But otherwise, it's not useful in today's conversation. We want to factor this the same way we factored the previous example, where you have some state gathering portions and you have some immutable zone in the back, which is stateless, right? The problem here is the big database. So the real question is, how do you make access to a large, constantly changing database stateless? There are two patterns I'm aware of. I don't like the second one, but I'm going to show you anyway because it does have uses. They're the timestamped data pattern and the snapshot pattern. I will caveat this, that this doesn't work for all systems. Specifically write-heavy databases, like if you were building a system to do like stock ticks, in like millions a second, I don't know if this will work. But for pretty much any system that's got a slow write stream, even multiple times a minute is fine for these patterns. You can get this to work. So what are these patterns? The one that I like the most is the timestamp data pattern. So in your table, you have a column that gives you a timestamp of when that data was written. And when you access data, you do it in 2 steps. And the 2 steps is what allows you to be stateless. The first step is to get the most recent timestamp of the data in the database. And then when you query the data, you pass that timestamp back in to ensure that you only get data as equal to or older than that timestamp. And that's what makes it stateless, right? Because if new data is added, that second query won't pull it, right? Now you might say, okay, well, great, like what does that really do for me? What it does for me is that you end up with a situation where for hours, you might be pulling that same timestamp. And so your cache gets full of service calls and functions that use that timestamp in their calculations. And then when a new entry gets written, let's say this is an email system, right? You get emails pretty frequently, but not every second. So imagine you're sitting there in your email system pressing F5 to refresh the system, right? Every time you hit F5, the system's going to call that get most recent timestamp method, and it's going to get the same timestamp. and then it's going to say, format my display, right? Get me all the message subjects, get me the senders, and format an output. That first one is going to be pretty quick because you're calling an indexed column, you're getting a pretty quick response. And then the second call is going to be cached. All the heavy stuff of fetching all the actual data and formatting the screen is going to be the same every time. So from your system's perspective, if you're running the email system, as the user is jamming an F5, you're just running that first query over and over again and saving a ton of calculation. But the second a new email comes in, you get timestamp 7. They hit F5, the first query returns 7 this time. You make the second call, that's uncached, the operation's performed, your data gets shown, they keep hitting F5, and your system only did one operation. Right? And so it can be really efficient, even in circumstances where this seems like it wouldn't work. Now that said, there's a better version of this that I like even more. And that's when you apply, oh shoot, I messed up my slides. Just for curiosity, this is like their simple SQL queries needed to do something like this. Pretty obvious stuff. You select the max timestamp from a table where entity equals B. Later on, I'll use IBM as an example. And then you select data from table where entity equals that entity, and the timestamp's less than that time. But, like I was saying, I prefer to apply this pattern to object stores. I think this is a lot nicer. So in this situation, you have two databases. You have a big immutable document store that contains documents that never change. It's an append-only immutable document store. And then you have a relatively tiny index over that has the entity, the timestamp, and then a pointer to the immutable document. And this is great because this database on the left, the relational table, can be distributed via CDN like all over the world, like I was saying, for a user settings database, so that you can pretty much guarantee rapid access to that. And it can be sharded too, right? This is like a really ideal database for replicating without a cache. And then the immutable document store, that's the big heavy thing. You probably don't want to CDN that around the world. Maybe you do, but maybe you want like one copy somewhere or a couple of copies in like a big data center. But that is perfectly cacheable because the items in that will never change. All right, so this is the pattern that I use in my mortgage-backed securities analytics system at Bloomberg. So I've got real-world experience with this. And if you can fit your problem to it, it has some great behaviors. There's also the snapshot data pattern. Now, I don't love this, but I use it in certain circumstances. So the snapshot pattern is where you have a canonical database that just for whatever reason cannot be adapted to the patterns I just described. Right? So how do you fit it into a system where you want to have stateless access? One thing you can do is you can have a snapshot service that reads the current state of the canonical database and writes an immutable document to a store similar to one I just described. Right? And then you run off that. I don't like this as much because it's harder to get cache commonality. This is really useful when you have like big jobs and you can take one snapshot and then use it a lot. But if you have like millions of customers and they're each making their own snapshot, it's not that great. The reason I think this is still useful is that I use this in Bloomberg for situations like the environment of the world. My group takes a snapshot of the world market every minute, and all customers use that data for that minute. And if something goes wrong and we can't take a new snapshot, we'll just use that 1 minute snapshot for maybe 5 minutes until we can get a new snapshot taken. I also use it, I think this is also a great pattern for dealing with external systems. If there's some system that you must use that's owned by another company or another group in your business and you can't push stateless design practices down, maybe you can use this pattern to interface with them. We also do this at Bloomberg for some groups. So what ends up happening, right? How do we make this work? Because we only really just spoke about the database. We didn't talk about the DB access service or the business logic service. For the purposes of conversation, let's simplify a little bit. We don't need 2 copies of application services. I was just trying to push the good behavior of sharing business logic amongst applications. What we do is we had this timestamp database, like I said. And the application service, which is the last block before you enter the immutable zone, will call the timestamp database the instant it gets a customer request and say, give me the most recent immutable document for IBM. Right? And so you end up with a flow like this. Customer says, give me the analyst reports. That turns into a method that's maybe get analysis IBM. That's a very stateful call, right? The data for IBM changes. Maybe there's a username as a parameter of that function as well. That's super stateful. And then you break that down into stateless components. You call the timestamp database, and you get an immutable document here that points to the current IBM data at this moment, which you then pass into the business logic service. So now the business logic service has a method with the same name, nearly, except its parameter now is not a like vague indicator. It is a specific chunk of data. And then it calls the database with just that URL. And so what's cool here is you can put caches in front of both of these things. Right? You can cache the database access, and then you can cache the service access on top of it, because the service knows that the data will never change. This is important. If the database doesn't give you that guarantee, you can't cache that second layer because the database could change. And so what we've now really learned is that you can cache in layers upward. If you go to the lowest level component in your system, make sure that access is stateless or immutable, you can chain upwards. There are some other benefits of timestamp data that I like. So what we just discussed was that database reads can be cached as well as any service that depends on it. Point-in-time access is trivially supported if you're able to keep that data around forever. The databases get kind of big when you do append-only stuff. But if you do keep that stuff around for a while, you can just query what the state of the data was a couple of months ago and see what your answer would have been. I don't actually recommend that, but it's technically possible. Batch jobs, this I do recommend. Batch jobs can freeze the timestamp that they're using to ensure consistency. At Bloomberg, we run like huge overnight runs, Monte Carlo simulations for hours, and we don't want data to change during that process. Normally, this is a pain, right? You have to like do extra work to get this kind of functionality. But when you use a system like this, you just don't use time.time or datetime.now when you make your queries. You just freeze it when the time your job started, and you're good to go. Rollbacks can be performed with a system-wide cap on timestamp. We had an issue once at Bloomberg where the ETL processes kind of went awry, and we had some bad data enter production. So we just capped the value of timestamp that any client could use to a time before the bad data hit production. And the problem went away until we recovered it. It was like fantastic. It really saved my, I don't want to say it. And then I also don't think this is a good feature either, but if you wanted to, you could do timed releases by future dated timestamps. Again, I wouldn't do that, but it's technically possible. Okay, so certain types of big, slow databases we've now accounted for, I think. And also some external systems. Not all external systems will let you use the snapshot pattern, but maybe you can, right? And like I said before, I don't have a solution to every problem, but this is where I'm trying to grow myself as an engineer, is like, how do I get more and more situations to become stateless? And how do I push that to my team members and the teams I'm working with? One thing we didn't discuss is software versions. I want to talk about that now. So yeah, what if you deploy a new version of this business logic service, right? Obviously, that cache isn't going to be correct anymore if you deploy a new version of code that changes the logic in that service. And so I didn't mention this before explicitly, but key generation in the cache is really important, right? So you have two services now, and so which service version is that cache entry for? It's ambiguous. Really what you have to do, and what we do at Bloomberg, is that we include the version of the service in the cache key. So the cache keys that we have are the service version, the request name, all the parameters of the request, the body of the request, all hashed together. I think it was probably obvious for most people, but it's worth stating explicitly. If you chain many services together, so my system at Bloomberg, there's dozens of services in the immutable zone. For the purposes of having a reasonable diagram to discuss, I cut it down a little bit. But you'll often have situations where there's many services in a chain that all are cached. In that situation, you actually need to include, the software version of all services in the chain. It's a little annoying. We accomplish this by having a load balancer that is kind of like Kubernetes. It's a proto-Kubernetes system that is aware of the state of all production service versions and also has a static map of which services depend on other services. And so it will enforce that if service A calls service B, both A and B's version will be included in the cache key. Now, you might say, like, well, Pete, how is this different than invalidation? It's not invalidation. Key generation is the only appropriate time to handle cache complexity. The only time. So keep that in mind. Okay, so what did we end up with here? I think this is actually pretty cool because let's say we did deploy a new version of that business logic service, right? For a lot of systems, deploying a new service version is like, we'll just wipe the cache and we're starting over again. And some of our colleagues spoke about how, have you ever had an issue because of a cold cache, right? But you don't really need to be in that situation. In a situation like this, when you deploy a new version of the business logic service, the database cache is still good, right? So you're not like paying like completely cold performance time. And if you have a deeper caching, if you have multiple layers, all those other caches are still good. It's just your one little chunks cache that got cleared. And so you get this resilient caching behavior. Additionally, if you roll back that service version, we've all done that, right? If you roll back that service, the old cache entries are still there, assuming your cache is big enough to have some LRU behavior where you have a couple of hours, right? And so, I've been in situations where I moved the service forward, and then I rolled back, and I cleared the cache in the process, and then I was in trouble because the cache was cleared. The rollback service was good, but the cache was now the problem. And in this kind of design, none of that happens. When you roll back, all those cache entries are still there, and you're still good, all right? So these are all of the major elements that I currently consider when I'm designing systems. And if you have any other things that you think I've missed, I'd love to hear it afterwards. I get that external systems are tough. I get that write-heavy databases really aren't covered at all. But I'm hoping that over time, the software engineering industry, similar to the automotive industry, starts to standardize in good patterns. Cars are good now. They weren't in the 90s, right? Cars in the 90s were like cell phones today. You needed them, they were awesome, but they would break all the time, or some app would stop loading, or you have to force close something. And I'm hoping that stuff like this can help move software engineering to that situation where software is more reliable, there's less weird behaviors. This isn't, obviously there's a lot of other areas of architecture that are outside of this that we need to, as an industry, kind of settle on. But I'm hopeful. So this is a highly simplified version of the system at Bloomberg that I operate and the type of designs that I push for. User settings are outside of the cache area. Same with the timestamps database for big databases. There's some very important portion of the system very early on. In an ideal world, the first service the client talks to, whose job it is to gather all that state, package it up, and then send it to the immutable backend that is as big as it can possibly be. Right, and that's the challenge there, is growing that space. So there's my, I allow for write-heavy databases. This is my last slide. I just want to go over the kind of big touch points one more time before I take questions. So true statelessness reduces total complexity. I think we showed that early on. Cache invalidation should just be a non-starter. If you find yourself, we might have systems that do that, right? But a good experiment, I think, to run is if you actually have active cache invalidation in your system, try to figure out what is the piece of state that is causing that. And ask, could you have applied one of these patterns to solve it? Maybe you couldn't, but maybe you could, and that could be a refactoring project for the future. Interface design drives cache characteristics. I think this is super important. Stateful interfaces can be converted into stateless ones, right? So don't give up if you are forced into an interface that is not natively stateless. And you can do that by factoring systems into stateful and stateless layers. Make low-level components stateless and chain upwards. And key generation is the right place to account for state. I will also say that one of the reasons I like talking about this stuff so much is because it is very difficult to retrofit this stuff afterwards, right? One of the things I love about this what I just showed in this diagram is that you get all sorts of incredible behaviors and you didn't really do anything, right? I didn't show up and say, we have this special component or this trick database or this globally synchronized clock. All I said was think about what your function parameters are, right? Be deliberate in how you structure stuff. And you get layered resilient caching. You get rollback supportable caching. You get all these nice behaviors. And you could just miss one of these details and the whole thing falls apart, right? And so it really is something that benefits from upfront thought. We're also hiring. I personally have spots available in my developer experience team. Like I said, we're here at SREcon, but we consider ourselves engineers first and foremost. Some of my teams are SRE teams. I have a DevX team as well. So I'm hiring for DevX. I'm also hiring for SRE. If you want to be in an organization that does maximally engineering-focused SRE, you can come talk to us. Many other groups are hiring as well in London, New York, all sorts of places. But that's it. I'm ready to take questions at this time.